Bismillahirrahmanirrahim. Assalamu alaikum everyone. I am here for the last lecture of this course, that was the Mgt605, and as usual I would like to give you a brief summary of the previous lecture, and after this we will continue our discussion as usual. And one thing will be extra in this lecture, that we will run through the whole summary of this 32 lectures. So I think you will enjoy and it will refresh your memory. So without going into detail, I would like to just give you the small and brief summary that we covered in the 31st lecture. If you remember, we talked about the panel data. Panel data is just an improvement over the other two kinds of data, the time series and the cross-sectional data. No something special with it, as it combines the, you can say, the information from cross-sectional and the time series data. So it is an improvement, and it has potential to address that issues that the only or the separate time series and the cross-sectional data are unable to perform. So this is very useful data, and one major advantage of this is as you pool the data, bring time series and cross-sectional data, then the number of observation increases, and you know, as the number of observation increases, the data becomes large, and it is very useful for the reliability of the results. In panel data, we talked about two major techniques. First was the fixed effect model, and the other was the random effect model. Both the techniques are based on some of the assumptions. So as the assumption change, they are targeting the similar things, but their assumption of based. Fixed effect model is based on many of the assumption, and similarly the random effect model is also based on many of the assumption. After this, we just have a touch to the simultaneous equation model. What was the simultaneous equation model as compared to the all previous discussion? In simultaneous equation model, there is not only the one-way causality, there may be the two-way causality. What this means, that the identification of the dependent variable becomes difficult, because the dependent variable is not only being influenced by the independent variable, but it also affects the dependent variable. It also has some effect on the explanatory variable. So there is a two-way, you can say, the situation, and it has some problem. So what was the problem? We said that if we apply OLS estimator without keeping in view that this variable is not determined only by this equation, but it may be determined by some other equation, so our estimates of OLS parameters are biased and inconsistent over time. So now, if you see that what we are going to do for this, we will be talking three topics. These topics are those topics that were missed, and we could not find any proper time to address this issue. These issues are important, they required, and we talked about these without giving much more justification. I talked about many times about the F-test and partial correlation, and I don't think that I talked about any of the time about the Jarque Berra test, but it is equally important, and you will see that this is a first measure that will immediately give you the right signal that whether you have completed your analysis in a proper way or is there any problem. After this, we will go through the whole course. We will take the important topics, and I will be giving you a very small introduction, and you can say the surroundings of those topics. So let us start that what is the Jarque Berra test. This is, you should keep in mind that this is a test of normality. What of normality? That our assumptions are normally distributed. So what this means, this is the test of normality, as you can say, I have just explained. This is a test of normality, and it is a large sample test. You can say the basic characteristic from the right beginning, that it is a test of normality and normality of the residual. and it is used, and it is more, you can say, it performs well when the you can say there is a large data, the number of observation is very large. It is based on the OLS regression residual. One, you can say, the good character, every characteristic is, you can say, the useful, but more useful characteristic of this is it is based on the residual of the OLS. So what this means, we need not to make some other estimation, and we will just concentrate on the OLS as we have done this, and this will give the information about the test on the basis of the OLS residual. This will help us that we need not some extra labor, extra effort to estimate the Jarque Berra test. This test first computes the skewness and kurtosis measures of the OLS residual. This is a pure statistical terms, that skewness and the kurtosis, and we will keep do not explain this. These are, you can say, the measures that are regarding to any of the variable, and the Jarque Berra test measures these skewness and kurtosis about the OLS residual. जब आप OLS रन करेंगे, वहाँ से residual आएंगे, and what is the residual? ui hat is equal to simply yi minus yi hat. So if this is the situation, that it means that it will calculate the kurtosis and the skewness of this OLS residual. And when we will be able to find this, we will be applying, we means the software applies this. This is the formula for the Jarque Berra test. If you look at this, where n is simply the sample size. If there are 80 observation, n is equal to 80. S is skewness coefficient, as you have calculated from there. What will be the value of the skewness about the residual term? This test will first calculate the skewness and the kurtosis, and k is kurtosis. So S shows skewness and k shows kurtosis. For a normally distributed variable, as we are seeing that we are looking at the variables that they should be normally distributed, and we are interested in that residual should be normally distributed. So what is the property of the residual distribution is that the normal distribution, that its skewness is equal to 0 and its kurtosis is equal to 3. There are formulas for k to compute kurtosis as well as the skewness, but we have nothing to do with this. We are just concentrating on this, that we reach and get the value of the Jarque Berra test. So if this will be the situation, we will say that for any of the normally distributed variable, its skewness should be equal to 0 and its kurtosis should be equal to 3. Therefore, the Jarque Berra test of normality is a test of joint hypothesis. यहाँ दो चीज़ें ज़रूरी हैं नॉर्मेलिटी assumption के लिए. हम भी बार बार कह रहे हैं कि नॉर्मेलिटी assumption we required about this one, about the situation of this and that. So the normality test, the Jarque Berra normality test is the, you can say, the giant test of giant hypothesis that S and K are 0 and 3 respectively. Because I have just explained that for normal distribution variable, normally distributed variable, its the skewness should be equal to 0 and k should be equal to 3. That is the kurtosis. So what this means, that the Jarque Berra test is trying to just simultaneously test these two assumptions, that is the S is equal to 0 and k is equal to 3. Under the null hypothesis, what is the null hypothesis? That the residuals are normally distributed. We assume, the Jarque Berra test assume that the residuals are normally distributed, and Jarque Berra showed that asymptotically Jarque Berra test follows the chi-square distribution with 2 degree of freedom. So what this means, our null hypothesis is that our means that null hypothesis of the JB test, Jarque Berra test, is that the residuals are normally distribution and it follows the chi-square distribution. So when it follows the chi-square distribution, it only says that we have to now see the very critical values from the chi-square distribution rather than the T, Z or F distribution. So what this means now, what is the rule of thumb? If the computed p-value of the Jarque Berra test, now rather than the chi-square values, I have deliberately in the last lecture I have written that p-value. P-value is obtaining the value of the statistics equal to or greater than that value, and you know when the p-value is less than 10, we reject the null hypothesis, and if it is greater than 10%, we do not reject the null hypothesis. If the computed p-value of the Jarque Berra test is sufficiently low in less than 10%, we reject the hypothesis. If this is the situation, we will say we will reject the null hypothesis. And what was the null hypothesis? That the residual are normally distribution. Indirectly we are saying that our residuals are not normally distribution, that our residuals are normally distributed and vice versa. We reject the hypothesis that the residual are, ये हमारा hypothesis था कि normally distributed हैं, but we reject this you can say the null hypothesis. And if the p-value is higher, greater than 10%, we do not reject the null hypothesis, and there is this inference that our residuals are normally distribution. So this was some of the mechanism of the this Jarque Berra test. Everything will be available as square. This is the kurtosis, and these values will be available. If rather than doing many of the values, taking S value, K value and what, I have just directly jumped towards the, you can say that we suppose that the value of Jarque Berra is 0.7769. That this statistics, the value of this is equal to 0.776. What this means, the p-value of obtaining such a value from the chi-square distribution with 2 degree of freedom is about 0.8%. This is the p-value of this, p-value of obtaining this value. This p-value has been obtained from the chi-square distribution with 2 degree of freedom, as we have explained that the Jarque Berra has showed that under the null hypothesis that the residuals are normally distribution, it follows the chi-square distribution. And if you go to the table for this reason, it is 0.6. Now my question is this p-value is very high or it is very small? You can say it is a very high p-value. तो फिर आप null hypothesis reject करेंगे or accept? Definitely you are unable to reject the null hypothesis. At the same time, now you are cheered, you are happy that you are not going to reject the null hypothesis, that was that the residuals are normally distributed. So it means indirectly we are accepting that yes, residuals are normally distribution because we are unable to reject the null hypothesis. In other words, we may not reject the normality assumption. It means if we are unable to reject the normality assumption, there is good news that the residuals are normally distribution. Of course, bear in mind the warning about the sample size. Again, I would like to say, though, in the very first line, if you see, we have said that the Jarque Berra test is an asymptotically large sample test, and if you apply it to the very small observation, it may not give the, you can say, the very critical or you can say very reliable result. So this is the, you can say, the last line is warning for you, and this is warning that if sample is small, you should avoid this. This is very, and what is my suggestion at this point is that whenever you run the regression, going for multicollinearity testing, heteroscedasticity, specification bias, the first and you can say the broader view or the broader indicator is the Jarque Berra test. If the value of the Jarque Berra test in p-value is very small, then it is dangerous. and if the p-value is high, then it is not dangerous. It shows that our residuals are normally distribution. In other words, I can say if the Jarque Berra value has small value, then it is not dangerous, but if it has higher value, as it will get the higher values, the p-value will come lower and lower, and ultimately you will be falling in the range of the rejecting the null hypothesis. Now, I think more than 10 times I said that I will be coming back on the F-test, so it is very important. This is the test, how to test the significance of the you can say the parameter. If you remember, we always most of the time we talked about the t-test, but due to many reasons in which we are not interested at this stage, we can say that we cannot use the usual t-test to test the joint hypothesis. Now what we want? We say that it is a very tedious and laborious work, that if we test, if there are 10, 20 or 50 estimators, now how will we be able to test one by one? T statistic lagaya, ek ko test kar liya ji hai ya nahi. Then again we will be going for this. So we were looking for some of the shortcuts that we put all things in one basket, and we decide that whether it is rejected or accepted. So the t statistics, due to some of the reason, is unable to test the joint hypothesis. However, the joint hypothesis can be tested by the F-test. So F-test has potential to test the, you can say, the situation in this way, that it can test the joint hypothesis. अगर आपके 20 betas हैं, तो ये उनको jointly जो है वो test कर देगा. I will be telling that how we form the null and the other hypothesis. Look at this. Given if we have this model, I will be writing it and explaining yi, and it is depending upon beta 1, beta 2, x2 and x2i plus beta 3, x3i, and it keeps on going up to beta n k xk. There are many, you can say, the variables. So there are how many betas? Beta are starting from 1 and they are going up to k. 1, 2, 3, 4 up to k. So what is this? To test the hypothesis, T mein hoga, if we apply t-test, we say in t-test we will make h0 that beta 1 is equal to 0 and beta 1 is not equal to 0. This will be our alternate hypothesis. हर एक के लिए हम 1, 2, 3, 4 up to k we will have to do this. But look at the F-test. To test the hypothesis, look at this. It is testing that all the parameters significance can be tested, you can say, jointly. For example, look at here. The null hypothesis of the F-test, not the t-test, is that beta 1 is equal to beta 2, beta 2 is equal to beta 3, and this is going on, and these are equal to beta k, and all are equal to 0. So this is very comprehensive, you can say, the null hypothesis, and against this the alternate hypothesis will be that these are not equal to 0. What this means? H1 will be beta 1 is equal to beta 2 is equal to beta 3, beta k is not equal to 0. This will be our, you can say, the null hypothesis. So it has jointly tested, and what will be the rule of thumb? Now look at this. These the slope coefficients are simultaneously 0. If I would like to explain this null hypothesis in sentence, I will say that the coefficients are simultaneous. Simultaneously mean at the same time are equal to 0. And h0, if I want to say that this h0 not all slope mean we are not testing the beta 1, but we can include that this is equal to beta 1. This, look at here, we started from beta 2 here, beta 2, 3, 4, beta 2, 3, 4. We are just testing the slope coefficient. What this means? Not all slope coefficients are simultaneously 0. Definitely, if our null hypothesis is that these slope coefficients are simultaneously equal to 0, definitely our alternate hypothesis is that these are not simultaneously equal to 0. Look at this. Here is the formula for this. It is very simple. Do you know what is the ESS? Yes, you know that it is the explained sum of square divided by the residual sum. This is the degree of freedom for this, the degree of freedom for the other. And this is further ESS over k minus 1, and the formula is this. By using this formula, you can find the value of the F test. That will be the computed value of the F test. Now apply your previous knowledge. Look at here. What is the rule of thumb? If F now mean is calculated, see here, is greater than F, this all means that the value of F, alpha is the significance level and this is the degree of freedom. Need not to worry that what is this. This is simply the F tabulated. This is the value of F from table, and definitely you will be supposing alpha at some level. You will have the k, the number of parameters, and the total number of observations. Now if F is greater than F calculated is greater than F tabulated, then you will reject the null hypothesis. And what was the null hypothesis? आपने कहा था कि ये सब जो slope coefficient हैं वो equal to 0 हैं. So we will reject this. We will say no, that these are not equal to 0. They are not showing that they are equal to 0. Otherwise, you do not reject. If situation is reversed, that F tabulated is less than F calculated, F calculated is less than F tabulated, we can't reject the null hypothesis. And what will be the result? That yes, all the parameters are equal to 0. So it is the Jan's test of significance, and you can say this is the k minus 1, this is, and the n minus k are only, these are the alpha level of significance, and k minus 1 numerator degree of freedom, and n minus k degree of freedom for this one. So I can give some example. For example, calculating each and everything, I say that calculated of value of F test, and its calculated value is, for example, 4.70. This for example, I use this formula, all this formula, and I read that there is FC calculated is equal to 4.70, and at alpha k minus 1 degree of freedom, I went to the table and I spotted that some level of significance on degree of freedom, the F tabulated value is 3.5. So what this means, now F calculated has become F tabulated, as its value is 3.5. So we will reject the null hypothesis, and it is nothing else. You can see the null hypothesis that all the coefficients are equal to 0. So this was the F test that for many times I talked about this. The difference between, or you can say the advantage of the F test, is that the T test, due to, you can say, some reason, is unable to jointly test the significance of the parameter. But F test has potential. It can simultaneously at the same time test the significance of, you can say, the any of the as many parameters as there are. Now there is, you can say, the other concept, that is the partial correlation. What is the partial correlation? You know the correlation. Correlation is simply the linear association between the variable. And if you remember, we denoted it by small r, and it is a measure or degree of linear association between two variables. So for the 3-variable regression model, if it was in the case of 2 variable, for the 3-variable regression model, we can compute 3 correlation. For example, if our model is, look at this model, yi is equal to beta 1 plus beta 2 x2 plus beta 3 x3 plus ui. This is our ui is always there before, when we still not estimate. When we estimate, this become go out of the van. Look at there, this is 1 variable, this is x2 another variable, this is the third variable. Now we can find, you can say, 3 variable regression model, 3 correlation. In this situation there are 3 correlation coefficient. What is this? इस मॉडल में क्या जी, पहला है जी R12. 1 we have given subscript to y, 2 to the x2, and 3 we will be giving to the x3. So R12, this is the correlation between y and x2. एक ये मेजर आ गई. R13, 1 for y, 3 for this. This is the correlation coefficient between y and x3. And R23, the correlation between x2 and x3. So what we are taking the pairwise correlation, and we are totally ignoring the third variable. So can it make some problem? We will see just now that is there any problem. The subscript 1 is, as you can say, this is 1, this we have attached with 1, this is 2 with this one. So R12 means the correlation between y, this is for y, this is for, you can say, x. R13, the correlation between y, and this is for the x3, this is for was the x2. R23, the correlation between x2 and x3. In general, R12 is not likely to reflect the true degree of association between y and x in the presence of yx2 and in the presence of x3. हम totally एक variable को ignore कर रहे हैं. When we are talking about that R12, it means it is the correlation between y and x2, and how it is not the true representative of the association, or you can the correlation, because x3 is also present. We are ignoring it, but it is present there. Therefore we use the partial correlation coefficient rather than simple correlation. We use the partial correlation coefficients for this. And now you will have to see some of the formula. Now I would like to just explain and then putting on you that how you use the formula. Look at this. यहाँ पर हमने कुछ चेंज कर दिया. पहले हम क्या करते थे? We would write only R12. Now we have given dot, and then we have said that it is 3 also there. Now the same thing, interpretation has become changed. Partial correlation coefficient between y, that is ये पहला subscript y, and x2, ये बात वही, holding x3 constant. We are now taking the you can say the taking the importance of x3 into the scene. In the previously we were ignoring it. दो के दरमियान देख रहे थे, तीसरे को जहन्नम में जाने देते थे. But here we are not ignoring this. We are saying that we are taking the correlation between 1 and 2, and we are holding the x3 constant. And here what this means? We are taking the correlation between 1, that is the y, 3 is the x3, and we are holding the 2, and this is partial correlation. So this was the partial correlation coefficient between y and x3 holding x2 constant. Only these terms have become more. And if this is R231, now what this is, 2 subscript is for x2 and 3 is for, you can say, the 2 subscript is for x2, this 3 is for x3, and this 1 is y. Every time I have to explain partial correlation coefficient between x2 and x3 holding y constant. So this was some of the interpretation, and you can say that it is better than R12, the R12, this one. This shows that this is the same thing. We are taking the correlation between this is for y, this is for x2. We are again saying here, but we are here bringing the x3 into picture, and we are saying that we are holding it constant. Now look at the formula. If you want to find this kind of formula, take the simple correlation between this one, and this one, multiply whatsoever is the situation. This is the formula, this is the formula, this. And using these formula, if you are a bit tricky, you will see that there is a link between the formulas. Look at here. Here 1, 2, here 1, 3. And what this here 1, 2 was? यहाँ भी 1 2 था, तो इसका मतलब है जो वहाँ 1 3 है ये यहाँ आ जाएगा, और यहाँ अगर 2 3 है तो पहले में 2 3. यू कैन लिंक द थिंग्स इन द सेम वे, सो इट इज अप टू यू, and I am completing the discussion on the partial correlation. Now I think the last half an hour we will be deputing towards the journey through the course, and you can see, if you look back, there was a long distance. We started in the beginning from the very first lecture when we and you were not much familiar to each other. Now you know that we and I am happy now we are much familiar with each other, and we have almost completed our journey, and we are just going to reach the final destination successfully. And I hope you have gone through all the course and you have learned from it. And just to remind some of the things, I would like to start from the very beginning, and I will go through this summary, and then we will be concluding. So as you know, the name of our course is the quantitative techniques. Quantitative techniques are used to analyze the data to bring the sum of the statistical inference, a quantifiable result. Rather than just talking about more or less, we want to see some of the figure. So there were also some of the, we compared the quantitative techniques and the qualitative techniques. That was, I think, not much difficult. The problem, the very interesting thing about the quantitative techniques was that how they proceed. They proceed in a very systematic way, and as you are completing one step, the other step, you are climbing in the right direction. So the first and the foremost, and every time I will emphasize that the first step, that how this quantitative methodology work, is that first of all we identify the problem. This is called the statement of the problem. First of all, we see that what is the problem. There are a number of problems. You should be very, very narrow in spotting your, you can say, the problem, and you should state in a very, you can say, a simple way. The next step was that when we have stated, the other was that we form a mathematical model. Mathematical model is not something special. We bring the notations into the mathematical notation, and it becomes mathematical model. And we can't estimate the mathematical model because this, in the social sciences, there is some chance of error. So this model, we have to introduce some of, you can say, the probability into the model. And the third step, that how the quantitative techniques work, the third step was that in this way we introduce the error term into this. You know that what is the error term. It captures many of the effect of the outside forces that are not in control. The fourth step in the quantitative technique, that how it developed, is the data collection. You know that when you made the statement, it was a theory. You linked the variable. Now you know the variable. You know where you want to get from data. Now you will be getting data about these variables. So this was the fourth step. The fifth step was, now we have to estimate the statistical model, or you can say the probability model. There are different techniques, but if you remember, most of the time we talked about the OLS estimator, because it is a very charismatic, you can say, the technique based on some of the assumption, and with very, very, you can say, the discrete and very powerful characteristics that the other may have not. The competitor was, you can say, the maximum likelihood method, but we did not bother about the maximum likelihood, and we kept on just building our whole discussion on the OLS. This was the fifth. And the sixth was, we estimated the model, and now we have to test the null hypothesis. It was the hypothesis testing, and we said we are now looking whether our parameters are statistically significant or they are statistically, you can say, insignificant. After this, making this assumption, the seventh was the forecasting or the prediction. We use these techniques that we could predict the value, average value of the dependent variable on the basis of independent variable. And the eighth and the last step in the methodology was that how to implement this. This is a very, very critical and difficult, because the many people means the stakeholder resist. For example, if in effective we say that the employees should be given double bonus, the management will resist. So our analysis is showing that as the bonus will be double, there may be the increase in the performance, but at the same time it is very difficult to implement. As you know, the government is saying that the minimum wage rate for the employee is 9,000, and now Nawaz Sharif and other companies have in their you can say the manifesto have said that the minimum wage for a laborer will be 15,000. These are a bit something, although these are not based on some of the analysis, but if these are drawn from some of the analysis, you can say it is very difficult to implement. This was how the quantitative techniques work. Now we are going towards the data. Data is simply the collection of information. There are two major kinds of data, the primary data and you can say that is the secondary data. Both data has their importance and both are useful in the micro data, or you can say the primary data. It may be useful in one circumstances, in the other you can say the other may be useful in that circumstances. So the reliability of data is very important. If your data is not reliable, the whole exercise will become futile. So you will have to be very careful before getting the data. But if it is secondary data, then you have no control over this. The data is available in the printing form and you will have to go for this. Then we talked about that for data collection, we are not supposing that you are going for the data that is micro data, or you can say the primary data. For this you will have to sample. Can you tell me that why you will be doing sample? What is different between the sample and the population? Population is the whole group about which a researcher is interested. For example, if I am interested in to study the behavior of the people of the capital Islamabad, this is the population. Now I cannot approach each and every person to see his behavior, any kind of behavior, consumption behavior, you can say the other kind of behavior. So for this we have to go the sample. The sample is the representative of the population. I am not talking about that the sample is of how much it is large, how much it is not. I am just talking about that the population, and then there is a sample. The simple answer that why we go from population to sample, the resources are limited and we have not enough time and money to study the whole population. And there is also possibility that the population is not the you can say static, it is dynamic, and as we complete our analysis, the population may have enter into some new regime that their behavior have changed. So we want to complete as quickly as possible. We talked about the infinite population. If it is countable, for example, if I see the number of living organism in the sea, so it is infinite population. But on the other side, if I say the number of animals in one district, this is countable and it is a finite population. Now, as we talked about the sample, there are sampling techniques. What is the sampling? That how you choose the sample, that whether it is very important, because if your sampling techniques are not correct, it will create some of the biases into your analysis, and that ultimately you will be falling into difficulty. So we talked about two major kinds of probability sampling. The first was that there is the probability sampling. The other was that there is the non-probability sampling. In probability sampling, we talked about many other things. What is the probability sampling? In selecting our sample size, if at any of the stage we use the concept of the probability, we will say that this is the probability sampling. And on the other hand, non-probability sampling, these are totally based on the discretion of the researcher, he or she is not using any kind of probability in spotting the sample. So within the probability sampling, there were many of the techniques. I would like to just give one or two names. The first was the pure random sampling. Very interesting technique, and everyone likes that there should be the random probability sampling. What this means, the selection of each and every unit in the population is equal as compared to its competitor. So random sampling is the best, you can say, the strategy if it is possible. Most of the time, due to many reasons, it is not possible. Then we talked about the systematic probability sampling. It is also, as I remember, I gave the example of that the outdoor patients and the people queuing up in the line, you can say, against any before any of the bank building. Then there was, you can say, multi-stage the cluster sampling, and there was also the stratified sampling, and you know what was the difference between this. The non-probability sampling, there was the quota sampling, there was the snowball sampling, and these were some of the, I need not to explain this. In the way of course, we also touched a mathematical concept, that was the derivative. We talked about many of the rules of the derivative that are not our interest at this stage. In the derivative is simply, it measures the rate of change in the dependent variable as a result of a change in the independent variable. So we applied in, you can say, the estimating, deriving our parameter that were the beta 1 hat and the beta 2 hat. After this, we started a very, very comprehensive topic, and that was the, you can say, the regression. In regression, we are interested in predicting the average value of the dependent variable on the basis of our independent variable. We talked about two kinds of regression. Most of the time, we talked about the simple regression model, in which only there were two variables. One was the dependent variable, and one was the independent variable. We build our whole theory on this simple the regression model, but later on we studied the three variable regression model, and sometime I wrote in which many of the variables were there, as you have just seen in the case of F statistics. We went up to K variable. And if you remember, going before the regression, we talked about the correlation. What is the difference between the correlation and the regression? In correlation, we just measure the degree of linear association between the variables, between the two variables. But here we are in regression, we are interested in measuring the average value of, we are interested in predicting the average value of the dependent variable on the basis of independent variable. So this, the correlation, what are the characteristics of some of the correlation? It ranges between -1 to 1. It means if it is 1, there is maximum, you can say, the positive correlation. If it is -1, there is the negative correlation. And if the correlation is 0, it means there is no linear association between the variable. So as it goes towards 1, the linear association increases. As it converts towards 0, the linear association becomes lower and lower. Then we talked about at least the 10 assumptions of the classical linear regression model on which we built our whole theory, particularly our estimator of OLS estimator. And I would like to just go through 2 or 3 assumptions that are the important. All the assumptions are important. The first assumption was that the independent variable are fixed. The other assumption was that the error term variance is constant over time. The other assumption in which we saw that there should be no multicollinearity, there should be no specification bias, and you can say we talked about that there is no autocorrelation. These were some of the assumptions of the classical linear regression model on which we built our theory over time. Then we talked about the OLS estimator. These are the ordinary least square estimator. They have some of the special characteristics, and they give a very charismatic results as we estimate our model based on the assumption of the classical linear regression model. And we talked about the three properties, that is the Gauss-Markov theorem, that the below property. What was this property? Below means best means that they have the minimum variance, and the linear means that there is a linear association, and unbiased means that if we take the expected value of those parameter, it will convert towards the true parameter. After this, we talked about the coefficient of determination. It is also called measure of goodness of fit. This tells us, measure of goodness of fit, it tells us that how our model is good. So this we denoted it by R square, and if you remember, from R square we went towards the adjusted R square. The difference between the R square and the adjusted R square is that R square increases when we include more independent variable into the model, whether they are relevant or irrelevant. But the adjusted R square has some cost benefit analysis, and it penalizes the researcher. And it also keeps in mind that as we increase this becomes, you can say, the R square becomes adjusted R square. So the measure of goodness of fit, adjusted R square, has the potential, it brings into account the loss of the degree of freedom. So we are just adjusted R square is the most reliable measure more reliable measure as compared to the R square. R square only tells us that how much proportion of dependent variable is being explained by our independent variable. So if its value is high, we say that our model is very good because it is explaining much more proportion. But it is only the higher R square is only you can say the suitable in the time series analysis. If in the you can say the panel estimation, if its value is lower, it is acceptable, but in time series data it is expected that its value will be higher. After doing this R square, and relating to adjusted R square, there is a game of maximizing the adjusted R square. I am not interested in telling you, but I would like to conclude at this time that only one thing you should remember, that the theory is much more important. Theory is important, and you can say the significance of your variable is important. This is, some people just bring more and more variable and keep to increase the R square. This is not recommended at this stage. The problems we talk about, that what are the problem of the regression model. We talked about the 4 problems of you can say the estimation problem. The first was the multicollinearity. Multicollinearity is simply that is there a perfect linear association between the independent variable, and if there is a perfect linear dependence between the variable, we are unable to estimate our result by OLS. So what this means, but if it is less than perfect, then you can say, it is interesting to note that still our OLS estimator are below, but you can't say that now they have larger variance, and the consequences of the larger variance. It has direct impact on the hypothesis testing, I think you know. Then we talked about the standardized variable. It was another way that when we have different kinds of variable in different, you can say the units and scale, we go for the standardized variable. And standardized variable are what? Simply, they are just, what is the definition of a standardized variable? When we subtract the mean of a variable from its each value and divide that difference by its standard deviation, it becomes the standardized variable. There is a very, very, you can say, useful benefit of this standardized variable, that when we standardize the data, then we can compare the magnitude or size of the coefficients directly. For example, if the magnitude of the parameter is higher, we can say that it has a higher effect on the dependent variable. And if you remember that if you And we also spent 1 hour or 1 lecture on the E-views. It was just a beginning, and I can say that I just taught you the ABC, and I will recommend for your future and for your survival in this, you can say, the changing modern technology, that although theory is important, but you will have to come up with the results. So if you have become more expert on the E-views, it is much beneficial for you people. Developing on this, discussing the regression and doing that and this and that things, we also went about the hypothesis testing. Hypothesis testing, it is only rules and regulation and the procedure of testing that whether our, you can say, the estimated parameter is significant or insignificant. In this process, if you remember, we were involved in constructing the confidence interval. When there is a two-tailed test, we say that there are 2 limits of the confidence interval, that one is the lower limit and one is the upper limit. And there was also a concept of alpha, that was the level of, you can say, the significance, and 1 minus alpha was the level of confidence, you can say, for this situation. Rather than going into detail, I would like to just make 1 or 2 sentences about the interpretation of the result. We say, first I will make the wrong statement. What people says, that there is a 90% probability that the estimated parameter will fall in this interval. No, this is not true, because either it is included in the interval or it is outside the interval. So we are talking about the probability of the confidence interval. Now I am going to make a correct statement, that where we are 95% confident that our constructed interval will include the true parameter. If we have made it on 95%, 90%, you can use for this. In hypothesis testing, there was one tail and two tail test. There was also a concept of p-value. So these are just refinement over this. Most of the time when we reject the null hypothesis, we say that our results are significant. And you know that if your value falls into the exception region, you are unable to reject the null hypothesis. If it falls on the extreme value, you can say that you reject the null hypothesis. There was a rule of thumb that if your calculated t-value, I am talking about now the t statistic, if that calculated t-value is greater than the tabulated t-value, then reject the null hypothesis. After completing the hypothesis testing, then appeared the dummy variable. Dummy variable is a different techniques from the, you can say, the other variable. What this means, dummy variable is not a ratio scale variable, it is a categorical variable in which there are categories. For example, gender is a ratio scale dummy variable which has 2 categories, male and female, and there are many other variables that we categorize. So the dummy variable, when we our dependent variable may be influenced not only by the ratio scale variable, but it may be influenced by the dependent variable. For example, if we look at the performance of the students, the male and female performance may be different due to many of the reasons. So now how to capture the male and female phenomena? We use the dummy variable and we use 0 and 1. 0 and 1 only is tradition. You can use other, you can say, the figure for this, and you will, 1 means most of the time, not again it is a sacred. 1 means that there is a presence. So in dummy variable we are just talking about whether it is present or not. If we say that it is 1, we will say that this category is present, and if we say that it is 0, we will say that it is not into the present there. ANOVA model war means, what this means, now I will be calling, this is the equation. If on the right hand side all the variables were dummy variables, then this kind of model is called the ANOVA model. If you can say that there are the mix up of you can say the dummy variables as well as the ratio scale variable, then we will call it that this is the ANCOVA model. So the only one thing about the dummy variable technique is that there is a dummy variable trap. We should avoid this dummy variable trap. What is the reason behind, what is this trap? That the people, there are two options that how to introduce dummy. The first is that introduce one less than the category, number of dummy variable should be less than one less than the category. अगर आपके पास 5 कैटेगरी हैं तो आपको 4 डमीज जो है वो यूज करने चाहिए. But sometime, and you can include the intercept, but if you are insisted that you do want to include that you can say that everything there, and you want to use as many dummies as their categories, then you will have to skip the intercept. And when you will skip the intercept, then your you can say the dummy variable are directly comparable. But when you are using one dummy less than the category, then the intercept is the base category. Intercept is the value of the base category, and you will be comparing the other categories with this, you can say, this category. So this was the, you can say, the dummy variable. After this, we went for the qualitative response model. अब एक बात आप याद रखें कि independent variable को भूल जाएं. Now we started a new discussion that was about the qualitative response variable. We said, we posed a question that if our dependent variable becomes dummy variable, then what will happen? Then there is, in the previous independent variable आपके dummy होते रहे, कोई issue नहीं है. OL, you can estimate it by OLS. But when your response variable or the dependent variable becomes the categorical variable, then there is a problem and we can't go for the OLS. Mechanically we can do, but there may be some problem. So we studied some of the other techniques. The first was the LPM. This was the linear probability model. It has the potential to address the issues that were faced by the OLS regression model. But at the same time, it is based on the probability at limits that the probability will remain between 0 and 1. And yes, probability remains between 0 and 1. The probability of occurrence of an event is 1, and occurrence of not occurrence is 1 minus pi. And if I say 1 plus 1 minus pi, it will be 1 minus pi. This is 1 minus, this will cancel out, and there will be the probability of this concept. Maybe you can say a bit confusing at this stage. So LPM and the linear probability model, it faced some of the, you can say, the problem. The one problem was that when we estimate, the values go beyond 0 and 1. And the other was that there is not the homoscedastic variance. The other was the R square becomes questionable. So this was the situation. For that we went for the Logit model. Logit model is based on you can say the cumulative distribution function, and this is the logistic cumulative density function. So we call it the Logit, and it rather than direct the linearity of the probabilities, it first measures the odd ratio and then go for the same procedure. On the same basis, there was the Probit model. There is a very small difference between the Logit and the Probit model. The Logit model is built up on the logistic cumulative density function, but the Probit model is based on the normal cumulative density function. There are many, you can say, the cumulative density function on which these can be built. So if this is the situation, in many of the situations the result for these three remains the same, but we are interested in largest and probit. The results are, you can say, the similar in many of the situation, and the people go for, the researcher go for the largest model because it is, you can say, the more mathematically comprehensible and it is easy to do this. After this, these were applicable when there was our dependent variable bicotomous. Bicotomous means only two categories, but it is not necessarily compulsion that it should be only bicotomous. It could be tricotomous, and it could be, you can say, the multicotomous or the polycotomous. If this is the situation, we go for the ordinal largest and ordinal probit model. The procedure will remain the same. Now I need not to go for again and again for the procedure. The process of the ordinal largest and ordinal probit is the similar, only now the difference has become that on the dependent side you can see that there are more categories of this kind. Then we also talked about, you can say, the multinomial largest and probit. This is another situation that in the previous largest and probit model, ordinal and largest and probit, we were assuming that the categories of the dependent variable are categorized, we can rank them. For example, strong, more strong, weak, more weak, we can this way. But if this is the situation that these categories are not rankable, for example, if I say I go to school on foot, on bicycle, on car and whatsoever, so these are not categorized. In this situation, we go for the multinomial largest and probit, and I think I should not give much discussion about the panel data because in the previous lecture you have done this, and this was the, you can say, the simultaneous equation model. So I will, at the end, I would like to say many thanks to you people who traveled a long journey with me. We started 32 lectures before, and now we are happy. I can see your face glaring, and I wish that you are going up and up in your career. And at this time, it is a time to say goodbye. So be happy, take care, goodbye, and Allah Hafiz.